right now, as you listen to this, somewhere in our galaxy, a cloud of gas colder than anything you have ever touched, colder than Antarctica, colder than liquid nitrogen, colder even than the vacuum of deep space itself, is quietly falling in on itself. It has been doing this for maybe 100,000 years. No one announced it. No one noticed. There was no flash, no sound, no signal of any kind. But inside that cloud, at this very moment, pressures are building that will eventually ignite a nuclear furnace 10 million degrees hot, and a new star will switch on for the first time, flooding a tiny corner of the Milky Way with light that has never existed before. And around that new star, a spinning disk of dust and ice will begin the slow, grinding work of assembling planets, moons, oceans, and possibly, given enough time and the right chemistry, life itself. Every atom of iron in your blood was forged inside a star that died before our sun was born. Every atom of oxygen in the air you are breathing right now was assembled in the heart of a massive star and scattered across space when that star exploded. And the nursery where all of this begins, the place where the raw ingredients of the cosmos are gathered together and compressed into something new, is a nebula, a stellar nursery, a glowing, sculpted, impossibly vast cathedral of gas and dust where the universe quietly, patiently builds its next generation of suns. This is the story of those places. This is the story of where stars come from, how solar systems are assembled, and why the very atoms that make up your body can trace their origins back to one of these luminous clouds. Hanging in the dark between the stars, we are going to travel deep into these nurseries. We are going to watch clouds collapse, see protostars ignite, and follow jets of superheated gas blazing through the darkness at hundreds of kilometers per second. We are going to stand at the edge of the pillars of creation and watch them being slowly devoured by the ultraviolet radiation of their own offspring. We are going to zoom into spinning disks of dust and ice where planets are being assembled right now, in real time, around stars that are younger than many species on Earth. And we are going to understand, perhaps for the first time, the extraordinary chain of events that had to unfold in order for you to be sitting here, listening to these words, made of atoms that were once adrift in a cold, dark cloud between the stars. It begins, as so many stories in physics do, with something invisible. If you could zoom out from the Earth, past the Moon, past Mars, past the orbits of the gas giants, and keep going until the sun itself was nothing more than a dim point of light lost among billions of others, you would eventually find yourself drifting through the interstellar medium. This is the name astronomers give to the vast, diffuse ocean of material that fills the space between the stars. It is not empty. Outer space, despite its reputation, is not truly a vacuum. It is filled with an extraordinarily thin haze of gas and microscopic particles of dust, spread so thinly that in some regions you might find only a single atom in every cubic centimeter of space. For reference, the air you are breathing right now contains roughly 25 quintillion molecules per cubic centimeter. The interstellar medium is, by any earthly standard, astonishingly sparse. And yet, it is nothing. This wispy material adds up across the immense distances between stars. And collectively, it accounts for roughly 10 to 15% of the visible matter in our galaxy. It is composed almost entirely of hydrogen, the simplest and most abundant element in the universe, making up about 70% of the interstellar medium by mass. Helium accounts for another 28%. The remaining sliver, roughly 1.5%, consists of heavier elements, things like carbon, oxygen, nitrogen, silicon, and iron, along with tiny grains of dust made from silicates and carbonaceous compounds. These heavier elements, every single one of them, were manufactured inside previous generations of stars and expelled into space when those stars died, either gently through stellar winds or violently through supernova explosions. The interstellar medium is not uniform. It has structure. It has texture. Some regions are blisteringly hot, heated to millions of degrees by the shockwaves from supernova explosions, filled with ionized gas that glows in X-rays. Other regions are warm and diffuse, with temperatures of a few thousand degrees. But the regions that matter most for our story are the cold ones. Scattered throughout the galaxy, embedded within this ocean of thin gas, are enormous structures called molecular clouds. These are the densest, coldest parts of the interstellar medium, and they are the raw material from which all stars are made. A giant molecular cloud is a staggering thing. A typical one might stretch 100 light years across, a distance so vast that light itself, traveling at 300,000 kilometers per second, would need a full century to cross from one side to the other. Inside, the gas is cold, extraordinarily cold, with temperatures hovering around 10 to 20 Kelvin. That is roughly negative 250 degrees Celsius, or about negative 420 degrees Fahrenheit. At these temperatures, hydrogen atoms pair up into molecules of molecular hydrogen, which is how these clouds get their name. Carbon and oxygen atoms similarly bond together to form carbon monoxide, and it is actually this carbon monoxide that astronomers most often use to detect and map molecular clouds. Since molecular hydrogen itself is extremely difficult to observe directly, the densities inside a molecular cloud are hundreds to thousands of times greater than in the surrounding interstellar medium, reaching perhaps 100 to 1,000 molecules per cubic centimeter. That is still an extraordinarily good vacuum by earthly standards, far emptier than the best laboratory vacuums we can create on Earth. But by the standards of interstellar space, it is remarkably crowded. And these clouds are massive. A single giant molecular cloud can contain anywhere from 10,000 to several million times the mass of our Sun. The Milky Way galaxy is estimated to contain around 6,000 of these giant molecular clouds, and together they hold roughly half of all the molecular gas in the galaxy. It is inside these cold, dark, enormous structures that the universe builds its stars. But the internal structure of a molecular cloud is far more interesting than a simple, uniform blob of gas. Modern observations, particularly those made with the Herschel Space Observatory in the far infrared, have revealed that molecular clouds are threaded with an intricate network of filamentary structures. long, narrow tendrils of dense gas that stretch across the cloud like the strands of a spider's web. These filaments are typically about 1/10 of a parsec wide, roughly 1/3 of a light year, and they can extend for many light years through the cloud. It is along these filaments, and particularly at the junctions where filaments intersect, that the densest concentrations of gas are found. And it is in these dense concentrations, called cores, that individual stars are born. The dust within these clouds, though it makes up only about 1% of the total mass, plays a role far out of proportion to its abundance. These dust grains, microscopic particles typically less than a micrometer in diameter, are composed of silicates, graphite, and various ices. They are the surfaces on which molecular hydrogen forms, because hydrogen atoms in the gas phase rarely collide with enough energy and the right geometry to bond together. Instead, they land on the surface of a dust grain, migrate across it, encounter another hydrogen atom, and bond together before being released back into the gas. Without dust, there would be no molecular hydrogen. Without molecular hydrogen, there would be no molecular clouds. And without molecular clouds, there would be no stars. Dust also plays a crucial role in cooling the cloud. As the gas contracts and heats up, the dust grains radiate that heat away in the form of infrared photons, which can escape the cloud even when visible light cannot. This radiative cooling allows the cloud to contract further without becoming too hot, maintaining the low temperatures necessary for gravity to continue its work. In a very real sense, dust is the air conditioning system of star formation, and without it, the process would stall. The interiors of these clouds are remarkably quiet places, shielded from the harsh ultraviolet radiation of the galaxy's hot stars by the outer layers of gas and dust. The innermost regions of a molecular cloud are among the coldest and most chemically rich environments in the universe. Over millions of years, the atoms and molecules within these protected zones undergo a rich chemistry, combining on the surfaces of dust grains to form increasingly complex molecules. Astronomers have detected over 200 different molecular species in interstellar clouds, including water, ammonia, methanol, formaldehyde, acetic acid, and even amino acids like glycine. The building blocks of biochemistry are being assembled in these dark, freezing clouds long before any star or planet exists to make use of them. But not easily, and not quickly. A molecular cloud, left to its own devices, does not simply collapse under its own gravity and produce stars. If gravity were the only force at play, every molecular cloud in the galaxy would have long since converted all of its gas into stars, and the night sky would look radically different from what it does. But gravity is not the only force at play. It has opponents, and those opponents are formidable. The first is thermal pressure. Even though molecular clouds are extremely cold, the gas particles inside them are still moving. They vibrate, they jostle, they bounce off one another. This random thermal motion creates an outward pressure that resists the inward pull of gravity. It is the same principle that keeps a balloon inflated. The gas inside pushes outward against the walls, and as long as the internal pressure balances the external forces, the balloon holds its shape. In a molecular cloud, gravity plays the role of the hand trying to squeeze the balloon, while thermal pressure plays the role of the air inside, pushing back. The second opponent is turbulence. Molecular clouds are not calm, static pools of gas. They are roiling, churning environments, shot through with supersonic currents and eddies, driven by a variety of external forces. Supernova blasts from nearby dying stars, the radiation pressure from luminous blue giants, the large-scale shearing motions of the galaxy's spiral arms, and the collision and merger of smaller clouds. This turbulence stirs the gas, preventing it from settling into the kind of dense, compact concentrations that gravity needs to trigger a collapse. The third opponent, and in many ways the most subtle, is the magnetic field. Molecular clouds are threaded by magnetic fields inherited from the broader galactic interstellar medium. These fields are weak by earthly standards, perhaps a few millionths of a Gauss, thousands of times weaker than a refrigerator magnet. But over the immense scales of a molecular cloud, they exert a significant influence. The ions within the cloud, the charged particles created by the feeble trickle of cosmic rays that penetrate even these dense environments, are coupled to the magnetic field lines and cannot cross them freely. The neutral particles, which make up the vast majority of the cloud's mass, are only loosely coupled to the ions through occasional collisions. This imperfect coupling creates a phenomenon called ambipolar diffusion, a slow leak of neutral gas across magnetic field lines that gradually allows gravity to concentrate matter. But it takes time, millions of years in many cases, for this process to tip the balance. So the cloud sits there, held in a precarious equilibrium between gravity pulling inward and pressure, turbulence, and magnetism pushing outward. It can remain in this state for millions of years, a cold, dark, seemingly inert mass of gas and dust, revealing no hint of the stars it will eventually produce. But eventually, something tips the balance. The British physicist Sir James Jeans worked out the mathematics of this tipping point in the early 1900s. He showed that for any given temperature and density, there exists a critical mass above which gravity will inevitably overpower thermal pressure and cause the gas to collapse. This critical threshold is now called the Jeans mass. For a typical molecular cloud core with a temperature of about 10 Kelvin and a density of around 10,000 molecules per cubic centimeter, the Jeans mass works out to be roughly a few solar masses. Any clump of gas exceeding this mass under these conditions will begin to collapse. But what pushes a region of a molecular cloud past this critical point? There are several possible triggers. A supernova explosion in the vicinity can send a shockwave slamming into the cloud, compressing regions of gas to densities high enough to initiate collapse. The collision of two molecular clouds can have the same effect. The expanding ionization front from a nearby massive star, blazing with ultraviolet radiation, can compress the surrounding gas like a plow pushing snow. Even the passage of a spiral density wave through the galaxy's disk can squeeze molecular clouds as they pass through the arm, nudging them toward instability. Once the collapse begins, it accelerates. As the gas falls inward, the density rises, which causes the gene's mass to decrease, which means smaller and smaller subregions of the collapsing cloud become unstable in turn. The cloud fragments, breaking apart into dozens or hundreds of smaller collapsing cores, each one destined to become an individual star or a small group of stars. This fragmentation is why stars almost never form in isolation. They are born in groups, in clusters, sometimes in vast associations of thousands of siblings, all emerging from the same parent cloud at roughly the same time. The evidence for supernova-triggered star formation is now quite strong in several specific regions of our galaxy. In the direction of the Cassiopeia constellation, a large shell of carbon monoxide emission has been identified that appears to be a molecular cloud compressed by the expanding remnant of a past supernova, with young stars forming along the compressed rim. Similar structures have been found near the Scorpius constellation. Laboratory experiments have even begun to simulate this process. In 2022, a team of researchers from institutions, including the Polytechnic Institute of Paris and the University of Oxford, used high-power lasers to create miniature blast waves that were driven into small foam balls, mimicking the interaction between a supernova remnant and a dense clump within a molecular cloud. The experiments successfully demonstrated the formation of compression waves inside the target, confirming that the physics of triggered star formation can be reproduced and studied in a controlled laboratory setting. These experiments represent a promising new frontier in laboratory astrophysics, allowing scientists to investigate the microphysics of star formation triggers that are otherwise impossible to study at full scale. The spiral arms of our galaxy also play a role. As molecular clouds orbit the center of the Milky Way, they periodically pass through the spiral arms, which are regions of enhanced gravitational potential. The compression experienced during this passage can trigger star formation on a galactic scale, which is why the spiral arms of galaxies like our own tend to be outlined by bright young stars and glowing emission nebulae. The pattern is visible in every spiral galaxy we can imagine. The arms light up with the blue glow of newly formed massive stars, while the regions between the arms are dominated by the redder light of older stellar populations. The collapse of a single core, from the moment gravity takes over to the moment a star ignites, takes on the order of a few 100,000 years for a core that will eventually become a star like our sun. For more massive stars, the process is even faster, sometimes as little as 100,000 years. In astronomical terms, this is remarkably swift. The galaxy barely has time to notice. The freefall time, the theoretical minimum time for a cloud to collapse under gravity with no resistance at all, provides a useful benchmark. For a typical molecular cloud core with a density of about 10,000 molecules per cubic centimeter, the freefall time works out to roughly 300,000 years. In reality, the collapse takes somewhat longer because thermal pressure and magnetic fields slow the infall, particularly in the outer regions of the core. But the order of magnitude is correct. A cloud core that today is a cold, dark, featureless concentration of gas will, in less than 1 million years, contain a glowing young star. The fragmentation of a collapsing cloud is a particularly fascinating phenomenon. As the cloud contracts and its density increases, the gene's mass decreases. This means that smaller and smaller subregions of the cloud become gravitationally unstable and begin their own independent collapse. The process cascades, producing a hierarchy of fragments from the largest scales down to the masses of individual stars. This hierarchical fragmentation is one reason why star-forming regions are so complex, with clusters of stars forming within clusters and dense subclusters embedded within larger, more diffuse associations. The masses of the resulting stars are not random. They follow a remarkably consistent statistical distribution called the initial mass function. First described by the astronomer Edwin Salpeter in 1955, the initial mass function tells us that low-mass stars are far more common than high-mass stars. For every star born with a mass greater than 10 times the Sun, roughly 1,000 stars are born with masses less than 1 solar mass. The peak of the distribution occurs at roughly 1/3 of the Sun's mass, meaning that the most common type of star produced in any star-forming event is a cool, dim, red dwarf, much smaller and fainter than our Sun. The physical reasons behind the shape of the initial mass function remain one of the outstanding questions in astrophysics, though it likely results from the interplay of gravity, turbulence, thermal physics, and magnetic fields during the fragmentation process. The dark cocoons. Before a molecular cloud core begins to collapse, before gravity wins its ancient war with pressure, there is a quiet stage that astronomers sometimes call the prestellar phase. And this phase has its own distinctive set of objects. Dark, cold, compact clouds that sit on the very edge of gravitational instability, trembling like a raindrop about to fall. The most striking of these objects are the Bok globules, named after the Dutch-American astronomer Bart Bok, who first drew attention to them in the 1940s. Bok and his colleague Edith Riley published a paper in 1947 in which they described these small, dense, dark clouds as the potential cocoons of future stars. They compared them to insect chrysalises, dark enclosures within which something remarkable was quietly taking shape. The comparison was remarkably prescient. Though it would take decades and the development of infrared and radio astronomy before their hypothesis could be confirmed, a typical Bok globule is small by the standards of molecular clouds, perhaps half a light year to a couple of light years across, with a mass of 2 to 50 times that of our Sun. They appear as strikingly dark silhouettes against brighter backgrounds of stars or glowing nebulae, blotting out the light of everything behind them. The reason they are so dark is simply that they are so dense. The dust grains within them, microscopic particles of silicate and carbon compounds, are packed closely enough together that they absorb virtually all of the visible light that tries to pass through. One of the most famous and best studied Bok globules is an object called Barnard 68, located about 400 light years from Earth in the constellation Ophiuchus. Through a visible light telescope, Barnard 68 is haunting. It appears as a perfect black void against the Milky Way's dense star fields, a hole punched in the sky. Not a single star is visible through its center. Its interior temperature hovers around 16 Kelvin, roughly -257 degrees Celsius, and its mass is about twice that of our Sun, packed into a region only about half a light year across. What makes Barnard 68 especially interesting to astronomers is that its edges are remarkably well-defined, and its density profile matches almost perfectly the predictions of theoretical models for a cloud on the verge of gravitational collapse. Observations suggest that Barnard 68 is gently oscillating, pulsing in and out like a slowly breathing organism, held in a knife-edge balance between gravity and pressure. Astronomers believe that within the next 200,000 years or so, the balance will finally tip, the cloud will begin to collapse, and a new star will be born from this dark, silent cocoon. When infrared telescopes are pointed at Bok globules, the picture changes dramatically. Infrared light, with its longer wavelengths, can penetrate through the dust that blocks visible light. In the infrared, the background stars reappear, reddened and dimmed by their passage through the dust. And in some globules, faint infrared sources appear deep within the cloud itself. The first warm glow of a protostar taking shape in the darkness. Surveys have found that over half of all known Bok globules contain newly forming stars. The cocoons are not empty. They are busy. And these globules exist not just in isolation. They are also found embedded within the larger structures of emission nebulae, where they appear as dark knots and pillars silhouetted against the bright glowing gas. In the Eagle Nebula, they appear as the dark globules at the tips of the famous pillars of creation. In the Orion Nebula, they are scattered throughout the cloud complex, each one a pocket of especially dense gas in which star formation is either underway or about to begin. These dark cocoons are the transition objects, the bridge between the vast, cold, relatively formless molecular cloud and the hot, luminous star that will eventually emerge. They are quiet places, invisible to the naked eye, unremarkable to a casual observer. But they represent one of the most consequential transformations in the entire universe, the moment when diffuse gas begins the irreversible journey toward becoming a star. What makes these objects so compelling to astronomers is that they represent a snapshot of a process that is otherwise almost impossible to observe in its entirety. A single molecular cloud core might take 1 million years to collapse from a diffuse concentration of gas into a fully formed star. No astronomer can watch a single core through this entire journey. Instead, astronomers study many different cores at many different stages and assemble them into a sequence, much like a biologist might study fruit flies at different stages of development to understand the process of metamorphosis. Bok globules, prestellar cores, Class 0 protostars, Class 1 protostars, T-Tauri stars, each represent a different stage in the same process, and together they form a narrative of stellar birth. The transition from a stable Bok globule to a collapsing prestellar core is not always a sudden event. Some globules oscillate for millions of years, gently pulsating in and out as gravity and pressure take turns, gaining the upper hand. During this time, the globule may slowly accumulate additional mass from its surroundings, or it may be nudged toward instability by an external perturbation, a passing shockwave, a collision with another cloud, or the tidal influence of a nearby star. At some point, the balance tips definitively, and the inward collapse becomes irreversible. The cloud contracts, heating slightly as gravitational energy is converted into thermal energy, and a dense, warm knot begins to form at the center. This is the prestellar core, the seed from which a star will grow. It is not yet a protostar. It has no internal energy source. It shines only by the feeble thermal radiation of its cold dust, but it is falling, and nothing will stop it now. The birth cry. Once a dense core within a molecular cloud crosses the threshold of gravitational instability, the collapse proceeds with gathering speed. The gas falls inward, accelerating under its own gravity. As it compresses, it heats up, the gravitational energy of the infall being converted into thermal energy. And because the collapsing cloud almost always possesses some small amount of rotation, a spinning motion inherited from the turbulent motions of the parent cloud, the material does not fall straight to the center. Instead, it flattens, conservation of angular momentum, forcing the infalling gas into a spinning disk around the growing central concentration of matter. This central concentration is the protostar, the embryonic star, not yet hot enough or dense enough at its core to ignite nuclear fusion, but growing steadily as material rains down onto it from the surrounding envelope and disk. In its earliest stages, the protostar is deeply embedded within its natal cocoon of gas and dust, completely invisible at optical wavelengths. It can be detected only through the infrared and submillimeter radiation emitted by the warm dust surrounding it. Astronomers classify these young stellar objects into a sequence of evolutionary stages based on how their emitted light is distributed across different wavelengths. The youngest, called Class 0 protostars, are so deeply buried that they emit almost all of their energy at far infrared and submillimeter wavelengths. They are surrounded by massive envelopes of infalling material and are actively building up their mass. A Class 0 protostar has accumulated less than half of its final mass and is still growing rapidly. This earliest phase is also the briefest, lasting perhaps 50,000 to 100,000 years, a blink of an eye in cosmic terms. It is so brief and so deeply embedded that observing it directly has been one of the great challenges of modern astronomy. As the protostar continues to accrete material, it transitions into the Class 1 stage, in which the surrounding envelope is thinner and the protostar begins to emerge, though it is still heavily obscured. The accretion disk surrounding the protostar is now well established, feeding material inward toward the growing star. And this is where one of the most spectacular phenomena of star formation occurs: the protostellar jet. As material spirals inward through the accretion disk, a fraction of it is redirected outward along the star's rotational poles. Launched at tremendous speeds, by the combined effects of magnetic fields and rotational forces. These jets are extraordinarily collimated, narrow beams of partially ionized gas shooting outward at velocities of 100 to over 1,000 kilometers per second. They can extend for light years on either side of the protostar, and when they slam into the surrounding interstellar medium, they create bright, glowing shock fronts. These shock fronts are called Herbig-Haro objects, named after the astronomers George Herbig and Guillermo Haro, who independently identified them in the 1940s. Herbig was studying star-forming regions in the Orion Nebula when he noticed small, bright patches of nebulosity with unusual spectra. Haro, working in Mexico, found similar objects around the same time. The Soviet astronomer Viktor Ambartsumian later gave these objects their formal name and was among the first to connect them to the earliest stages of stellar evolution. Herbig-Haro objects are transient. They last only a few tens of thousands of years before the jet material disperses and fades. But during their lifetime, they serve as brilliant signposts, announcing the birth of a star to anyone who knows where to look. They come in a dazzling variety of shapes: bow shocks, knots, chains, filaments, and wispy arcs, each one tracing the complex, pulsing, sometimes processing flow of the jet. The jets are not continuous streams. They erupt in pulses, as the accretion rate onto the protostar varies over time, producing clumps of faster and slower material that interact and collide within the jet itself, creating the internal shocks that give many Herbig-Haro objects their knotty, beaded appearance. The discovery of Herbig-Haro objects represented a major conceptual breakthrough in our understanding of star formation. Before their nature was understood, astronomers had assumed that the formation of a star was essentially a process of pure infall, with material flowing only inward toward the growing protostar. The discovery that a significant fraction of the accreting material is actually ejected outward, perpendicular to the disk, at enormous velocities, was unexpected. It is now understood that this outflow is not merely a byproduct of the accretion process, but is intimately connected to it. The jets help to remove angular momentum from the infalling material, allowing it to spiral inward through the disk more efficiently. Without the jets, the angular momentum barrier might prevent much of the material from ever reaching the star. In a sense, the star must throw away material in order to grow. It must lose in order to gain. The total number of known Herbig-Haro objects has grown steadily over the decades. By the mid-1990s, several hundred were cataloged. Today, well over 1,000 individual HH objects or groups have been identified, and the number continues to grow as new infrared and submillimeter surveys probe deeper into the dustiest star-forming regions. Some of the most spectacular examples stretch for several light years, their bow shocks plowing through the interstellar medium far from the parent star that launched them. Others are tiny, compact nebulae barely resolvable in even the most powerful telescopes. All of them tell the same story. A young star is forming nearby, and it is announcing its arrival with spectacular violence. As the protostar matures and the surrounding envelope of infalling material is gradually consumed or blown away by the jet and by radiation pressure. The young star enters the T Tauri phase. T Tauri stars are named after the first recognized member of the class, the variable star T Tauri in the constellation Taurus, which was found to be a very young star, still in the process of contracting toward its main sequence configuration. T Tauri stars are the teenage years of solar mass stars. They are still surrounded by circumstellar disks, though the massive envelopes of their earlier phases have dissipated. They are prone to dramatic outbursts and variability, their surfaces roiled by powerful magnetic fields, and their disks occasionally dumping surges of material onto the stellar surface. They drive winds and outflows, though less powerful than the jets of their protostellar youth. Studies suggest that roughly 60% of T Tauri stars younger than 3 million years still possess dusty disks, compared to only about 10% of those that are 10 million years old. The disks are slowly being consumed, their material either accreted onto the star, blown away by radiation, or, in some fortunate cases, assembled into planets. The T Tauri phase lasts roughly 10 to 100 million years, depending on the mass of the star, after which the star settles onto the main sequence and begins the long, steady era of hydrogen fusion that will define the majority of its lifetime. But during those restless, turbulent early years, surrounded by a disk of debris, and possibly by newly formed planets, the young star is still very much a creature of its nursery. It is still embedded in or near the molecular cloud from which it was born, still linked to its siblings by the residual gas and dust that connects them, still subject to the gravitational influences of its neighbors. The great nurseries. Not all stellar nurseries are created equal. Some are modest affairs, small molecular cloud cores producing a handful of low-mass stars in relative isolation. Others are titanic engines of creation, producing thousands of stars across regions spanning dozens of light years, their interiors sculpted by the fierce radiation and powerful winds of the most massive stars they have produced. The most famous stellar nursery in the sky, and one of the most studied objects in all of astronomy, is the Orion Nebula, also known as Messier 42, visible to the naked eye as a fuzzy patch of light in Orion's sword. Just below the 3 bright stars of Orion's belt, the Orion Nebula is an enormous cloud of glowing gas, roughly 24 light-years across, located about 1,350 light-years from Earth. It is the closest massive star-forming region to our solar system, and its relative proximity has made it an invaluable laboratory for studying the birth of stars and planetary systems. The nebula that we see glowing in visible light is actually just a thin, ionized blister on the near surface of a much larger, much darker molecular cloud called the Orion Molecular Cloud Complex. This complex extends across a significant fraction of the constellation Orion and contains enough gas and dust to make tens of thousands of stars. The visible nebula is essentially a cavity that has been hollowed out of the front face of this cloud by the ultraviolet radiation and stellar winds of the hot young stars within it. We are looking at the illuminated wall of a vast cavern, with the dark molecular cloud stretching away behind it into the distance. The history of human observation of the Orion Nebula stretches back centuries. The Mayan civilization of Central America appears to have been aware of the nebulosity, incorporating it into their cosmology as a region associated with cosmic fire and creation. European astronomers first noted it telescopically in the early 16th century. The French astronomer Nicolas Claude Fabry de Peiresc is generally credited with the first telescopic observation in 1610, though the Dutch scientist Christian Huygens produced the first detailed sketch and description in 1656. It was Charles Messier who assigned it the catalogue number M42 in 1769, making it one of the most well-known entries in his famous catalogue of nebulous objects. At the heart of the Orion Nebula lies the Trapezium cluster, a tight group of hot, luminous young stars discovered by Galileo Galilei in 1617. The four brightest stars of the trapezium form a distinctive trapezoidal pattern visible in small telescopes. These are massive stars, ranging from about 15 to 30 times the mass of our Sun, and they are extraordinarily young, no more than about 300,000 years old. Their intense ultraviolet radiation ionizes the surrounding gas, causing it to glow with the characteristic colors of hydrogen, oxygen, and sulfur that make the nebula so photogenic. The brightest of the trapezium stars, Theta 1 Orionis C, is an O-type star roughly 251,000 times more luminous than the Sun. One of the most luminous stars known in our region of the galaxy, the Trapezium cluster, is itself embedded within the larger Orion Nebula cluster, a grouping of about 2,000 stars occupying a region roughly 20 light-years in diameter. The star density in the immediate vicinity of the trapezium is among the highest of any known star-forming region. And scattered throughout this cluster, revealed by the Hubble Space Telescope in the early 1990s, are nearly 200 protoplanetary disks, dark silhouettes seen against the bright background nebula. These proplyds, as they are called, are the circumstellar disks of young stars, caught in the act of being slowly eroded by the trapezium's fierce ultraviolet radiation, even as they attempt to assemble planetary systems. Several thousand light-years farther away, in the constellation Serpens, lies another legendary stellar nursery, the Eagle Nebula, Messier 16. This nebula achieved global fame in 1995 when the Hubble Space Telescope captured an image of its interior that would become one of the most iconic photographs in the history of science. The image showed 3 towering columns of gas and dust, sculpted by the ultraviolet light and winds of a nearby cluster of hot young stars, their edges glowing, their surfaces studded with tiny dense knots where new stars were forming. The image was called the Pillars of Creation, and it instantly became a symbol of the beauty and violence of star formation. The pillars themselves are composed of cold molecular hydrogen and dust. The tallest of them is roughly 4 to 5 light-years in length, larger than the distance from our Sun to the nearest star. The finger-like protrusions at their tips are made visible by the shadows of small, dense globules called evaporating gaseous globules, or EGAS, which shield the gas behind them from the intense ultraviolet radiation. Some of these eggs contain protostars within them, embryonic stars forming even as their natal material is being stripped away by the hostile environment. It is a race against time. The protostar must accumulate enough mass to ignite fusion before the surrounding gas is completely evaporated by the nearby cluster of massive stars. Some will succeed, others will be left as orphaned, low-mass objects, perhaps brown dwarfs, objects too small to sustain hydrogen fusion, but too large to be called planets. Forever stranded between categories, the Eagle Nebula itself spans about 70 by 55 light-years and lies roughly 5,700 light-years from Earth. The star cluster at its center, NGC 6611, is estimated to be only 1 to 2 million years old. Its stars so young that many still retain the dusty disks from which planets might eventually form. The brightest star associated with the nebula has a mass of about 80 times that of the Sun and a luminosity approaching 1 million times solar. The cluster contains approximately 8,100 stars in total, the vast majority of which are far less massive than the luminous giants that dominate the visible appearance of the nebula. In October 2022, the James Webb Space Telescope revisited the pillars of creation with its powerful near-infrared cameras, producing an image that pierced through the obscuring dust to reveal a wealth of previously hidden stars forming within the pillars. The new image showed hundreds of stars that had never been seen before, glowing red points of light embedded in the dusty columns, each one a sun in the earliest stages of its existence. Even more spectacular, in a different way, is the Carina Nebula, one of the largest and brightest nebulae in the sky, located roughly 7,600 light-years away in the southern constellation Carina. This enormous complex spans over 300 light-years and is home to some of the most massive and luminous stars in the galaxy, including the famous Eta Carini, an unstable supergiant star with a mass roughly 100 times that of the Sun that is expected to explode as a supernova sometime in the next few 100,000 years. The Carina Nebula was one of the first targets of the James Webb Space Telescope when its initial images were released in July 2022. The image of the region designated NGC 3324, dubbed the Cosmic Cliffs, instantly became one of the most shared and discussed astronomical images in history. It showed the edge of a gigantic gaseous cavity being sculpted by the radiation of hot young stars, its ridges and towers stretching 7 light-years high, with hundreds of previously hidden young stars revealed for the first time in the infrared. But the true scientific value of the Cosmic Cliffs image went far beyond its visual impact. When astronomers dug deeper into the data, separating out individual wavelength channels and examining specific molecular emission lines, they found something extraordinary. Hidden within the dusty ridges of the Cosmic Cliffs were more than 24 previously unknown jets and outflows from young stars. none of which had been visible in earlier Hubble observations. These jets traced the earliest, most active phases of star formation, when protostars are still rapidly accreting material and launching powerful bipolar outflows. The JWST's sensitivity to molecular hydrogen, a key tracer of star-forming activity, allowed researchers to map these outflows in exquisite detail, revealing the complex, turbulent interactions between the jets and the surrounding molecular gas. By comparing the new JWST observations with earlier Hubble images taken 16 years prior, astronomers could even measure the speed and direction at which the jets were moving, tracking their evolution across time. These measurements provided crucial data for understanding how protostellar outflows develop and how they shape the environments around young stars. The Rosette Nebula, located about 5,000 light-years from Earth in the constellation Nurseries, offers a different perspective on the star formation process. This vast emission nebula, roughly 130 light-years across, has a distinctive circular shape created by the stellar winds and ultraviolet radiation of the hot young stars at its center. The rosette contains enough gas and dust to form roughly 10,000 stars like our Sun, making it one of the most massive stellar nurseries in our region of the galaxy. The open cluster NGC 2244, sitting within the nebula's cleared central cavity, contains massive O-type stars whose fierce winds have blown a bubble in the surrounding gas, compressing it into a dense ring where new generations of stars are now forming. The most massive of these stars, with masses up to about 50 times that of the Sun, are the engines driving the nebula's evolution, their radiation ionizing the surrounding hydrogen and causing it to glow with the characteristic red light that gives the rosette its vivid color in astrophotographs. Roughly 2,500 young stars have been identified within the rosette complex, and Chandra X-ray observatory observations have revealed that star formation is still actively ongoing in the dense molecular gas surrounding the central cavity. Dark filaments of dust extending toward the center of the nebula, sometimes called elephant trunks, are shaped by the stellar winds and electromagnetic forces from the hot young stars, and represent dense pockets of gas where the next generation of stars may already be taking shape. And then there is the Tarantula Nebula, also known as 30 Doradus, the most intense star-forming region in the entire local group of galaxies, located not in the Milky Way, but in the Large Magellanic Cloud, a satellite galaxy roughly 160,000 light-years distant. The Tarantula Nebula is so luminous that if it were placed at the distance of the Orion Nebula, it would fill the sky equal to 60 full moons and cast visible shadows on the ground at night. At its center lies the cluster Roan 136, a dense concentration of some of the most massive stars ever discovered, including several with masses exceeding 100 times that of the Sun. The tarantula represents the kind of extreme, starburst-style star formation that was far more common in the early universe, making it a uniquely valuable laboratory for understanding how galaxies assembled their stellar populations billions of years ago. What makes the tarantula especially significant is its chemical composition. The Large Magellanic Cloud contains only about half the abundance of heavy elements found in the Milky Way. This makes its star-forming conditions much more similar to those that prevailed in the early universe, when galaxies were young and had not yet been enriched by many generations of stellar nucleosynthesis. By studying how stars form in the tarantula under these more pristine conditions, astronomers can gain insight into the processes that built the first generations of galaxies. The nebula appears to have come to life 20 to 30 million years ago, when the first major burst of star formation began. Since then, multiple generations of massive stars have formed, lived, and died within its boundaries. Astronomers estimate that between 40 and 60 supernovae have already detonated within the older cluster, Hodge 301, located at the nebula's edge. The shockwaves from these explosions have compressed gas on the outskirts of the central cluster, NGC 2070, helping to jumpstart new waves of star formation in a continuous cycle of creation and destruction. The Lagoon Nebula, or Messier 8, offers yet another window into the diversity of stellar nurseries. Located about 4,000 to 5,000 light-years from Earth in the constellation Sagittarius, the Lagoon Nebula gets its name from the distinctive dark lane of absorbing dust that bisects its bright interior, creating the appearance of a lagoon-like channel running through the glowing gas. The nebula spans roughly 110 by 50 light-years and is powered by the hot young star Herschel 36, a massive O-type star whose fierce radiation is sculpting the surrounding gas into dramatic ridges, furrows, and tornado-like funnels of twisted gas. The Lagoon Nebula is one of only 2 star-forming nebulae visible to the naked eye from mid-northern latitudes, the other being the Orion Nebula. Through binoculars on a clear night, it appears as a faint, milky glow in the dense star fields of the summer Milky Way. Telescopic images reveal a seething, turbulent environment where ultraviolet radiation is boiling the surrounding gas, heating it to temperatures of thousands of degrees, and launching dramatic jets and flows from the protostars embedded within the cloud's denser regions. Each of these nurseries, from the modest nearby Taurus star-forming region to the titanic Tarantula Nebula, represents a different face of the same fundamental process. The physics is the same. Gravity pulls gas together. Pressure resists. Something tips the balance. The cloud collapses, fragments, and produces stars. But the scale, the intensity, the number and mass of the stars produced vary enormously from one nursery to the next, shaped by the initial conditions of the cloud, its mass, its density, its temperature, its rotation, its magnetic field strength, and the external forces that disturb or compress it, the spinning cradle. As a molecular cloud core collapses to form a protostar, conservation of angular momentum dictates that the infalling material cannot simply plunge straight to the center. Any small amount of rotation in the original cloud, and some rotation is almost always present, is amplified enormously as the cloud shrinks, just as an ice skater spins faster when she draws her arms to her chest. The result is that the collapsing material flattens into a rotating disk around the central protostar, a protoplanetary disk. And it is within this disk that the raw materials for planets are gathered, and the first stages of planet formation begin. A protoplanetary disk is typically a few hundred astronomical units across, where 1 astronomical unit is the distance from the Earth to the Sun. The disk is composed of roughly 99% gas, mostly hydrogen and helium, and about 1% dust, the tiny grains of silicates, carbon compounds, and ices that were present in the original molecular cloud. This 1% of dust is crucial because it is from this dust that rocky planets like Earth and the solid cores of gas giants like Jupiter are ultimately assembled. The disk is not uniform in composition. Closer to the star, where temperatures are high, only refractory materials like metals and silicates can survive in solid form. Water and other volatile compounds are vaporized. Farther out, beyond a boundary called the snow line or frost line, temperatures are low enough for water ice to condense. This fundamental temperature gradient, hot near the star and cold farther away, plays a decisive role in determining what kinds of planets form at different distances. Rocky, dense terrestrial planets like Earth, Venus, Mars, and Mercury form inside the snow line, where only rock and metal can condense. Gas and ice giants like Jupiter, Saturn, Uranus, and Neptune form beyond it, in the regions where abundant ice adds to the available solid material and allows planet cores to grow large enough to gravitationally capture thick atmospheres of hydrogen and helium. The process of planet formation within these disks is thought to begin with the slow growth of dust grains. Microscopic particles of dust collide and stick together, building up over time into larger and larger aggregates. From micron-sized grains, they grow into millimeter-sized pebbles, then centimeter-sized clumps. Getting from centimeters to kilometers, the size range of planetesimals is one of the most active areas of research in planetary science, because at intermediate sizes, the particles face several barriers. They tend to bounce off each other rather than stick, and the gas drag from the disk can cause them to spiral inward toward the star rather than continuing to grow. Several mechanisms have been proposed to bridge this gap, including the streaming instability, in which concentrations of pebbles become dense enough to collapse directly under their own gravity, forming planetesimals in a single step. In 2014, the Atacama Large Millimeter/Submillimeter Array, known as ALMA, produced an image that transformed our understanding of protoplanetary disks. ALMA observed the young star HL Tauri, located about 450 light-years away in the constellation Taurus, and revealed its protoplanetary disk in stunning detail. The image showed a series of bright concentric rings separated by dark gaps, a structure that bore an uncanny resemblance to the grooves of a vinyl record. The gaps were widely interpreted as evidence that planets had already formed within the disk and were carving out lanes in the dust through their gravitational influence. What made this discovery so startling was the age of the system. HL Tauri is only about 1 million years old, The conventional wisdom had been that planet formation was a slow process, taking tens of millions of years. The ALMA image suggested that it could begin far earlier than anyone had expected. Subsequent observations have confirmed that rings and gaps like those in HL Tauri are not anomalies. They are common. A large survey called DSHARP, conducted with ALMA in 2018, found that such substructures are widespread in protoplanetary disks, appearing in disks of widely varying sizes, ages, and environments. More recent work, published in 2025 by a team led by Santiago Orcajo, used ALMA data and advanced simulations to trace the evolution of these disk structures through 5 distinct stages, providing strong evidence that the rings and gaps are indeed carved by forming planets gravitationally interacting with the surrounding dust and gas. These spinning disks, these protoplanetary cradles, are the construction sites of solar systems. They are where the building blocks of planets are sorted, concentrated, and assembled. They are where the chemistry of future worlds is determined, where the ratio of rock to ice to gas is set by the simple physics of temperature and distance. And they are remarkably common. Observations suggest that essentially every young sun-like star is surrounded by a protoplanetary disk during its first few million years. Planet formation is not a rare event. It is a natural, almost inevitable consequence of the star formation process itself. But protoplanetary disks do not last forever. They are gradually depleted by a combination of processes: accretion onto the central star, incorporation of material into planets and planetesimals, and dispersal by the star's own radiation. As the star settles onto the main sequence and its luminosity stabilizes, the increasing flux of ultraviolet and X-ray photons heats the disk's surface layers, causing gas to evaporate away from the disk in a process called photoevaporation. This process, working from the outside in and from the inside out simultaneously, gradually strips the disk of its gaseous component, leaving behind only the solid material that has already been incorporated into larger bodies. The typical lifetime of a protoplanetary disk is about 2 to 3 million years, though some persist for as long as 10 million years. After the gas is gone, what remains is a debris disk, a thinner, dustier structure composed of the leftovers of the planet formation process, asteroids, comets, and the fine dust produced by their mutual collisions. Our own solar system retains 2 such debris structures: the asteroid belt between Mars and Jupiter, and the Kuiper belt beyond Neptune. Recent ALMA observations from the ARC survey, published in 2026, have studied 24 exo-Kuiper belts in unprecedented detail, revealing that these teenage debris disks are much more unsettled than previously thought, with structures pointing to the ongoing presence of planets that are still shaping their environments. The transition from a gas-rich protoplanetary disk to a gas-poor debris disk marks a critical turning point in the life of a planetary system. Once the gas is gone, the gravitational architecture of the system is largely fixed. The giant planets have formed, or they have not. The rocky planets have accreted their final masses, or they have not. The water and volatile compounds that will determine the habitability of inner planets have either been delivered or have not. Everything that follows, the billions of years of planetary evolution, the emergence of atmospheres and oceans, and possibly life, depends on decisions made during these first few million years. In the spinning disk surrounding a newborn star, for most of human history, stellar nurseries were invisible. The dense gas and dust that make them what they are also make them opaque to visible light. The glowing emission nebulae that we can see with our eyes, the Orion Nebula, the Lagoon Nebula, and the Eagle Nebula, are only the surfaces of much larger structures. They glow because the ultraviolet radiation from hot young stars ionizes the gas at the cloud's surface, causing it to emit light. But behind that glowing surface, deeper within the cloud, the dust blocks our view completely. For centuries, astronomers could see the results of star formation, the bright young stars, and the glowing gas they illuminated. But the actual process of star formation, the collapse, the accretion, the disk formation, remained hidden behind an impenetrable curtain. The revolution began with the development of infrared astronomy in the mid-20th century. Infrared light, with its longer wavelengths, can pass through dust much more easily than visible light. Just as red light penetrates fog more effectively than blue light, the first infrared surveys of star-forming regions revealed a population of objects that had no visible counterparts at all, deeply embedded protostars that were completely invisible to optical telescopes, but blazing brightly in the infrared. These were the youngest stars, still wrapped in their natal cocoons, and for the first time, astronomers could observe them directly. The earliest infrared observations of star-forming regions were crude by modern standards, limited by the sensitivity of the detectors and the blurring effects of the Earth's own atmosphere, which itself emits infrared radiation. But even these primitive observations were revelatory. In the early 1960s, two astronomers named Eric Becklin and Jerry Neugebauer pointed an infrared detector at the Orion Nebula and discovered a bright source that was completely invisible at optical wavelengths. This object, now known as the Becklin-Neugebauer object, or BN object, turned out to be a massive young star still deeply embedded in the molecular cloud behind the visible nebula. Its discovery was among the first concrete demonstrations that star formation was happening in places that could not be seen with traditional optical telescopes, and it helped to establish infrared astronomy as an essential tool for understanding the birth of stars. Radio and submillimeter astronomy opened another window. At these very long wavelengths, dust is essentially transparent, and the cold molecular gas that makes up the bulk of molecular clouds can be directly observed through its characteristic emission lines. Carbon monoxide, in particular, became the primary tracer of molecular gas in the galaxy. The first detection of carbon monoxide in a star-forming region was made in 1970 by Arno Penzias, Keith Jeffords, and Robert Wilson, working at the Bell Telephone Laboratories when they identified co-emission from the Omega Nebula. This discovery opened the floodgates. carbon monoxide is far easier to detect than molecular hydrogen, and within a few years, radio astronomers had mapped hundreds of molecular clouds throughout the galaxy, revealing the full extent of the raw material available for star formation. By mapping the distribution of carbon monoxide emission, astronomers could chart the structure of giant molecular clouds in 3 dimensions, measuring their masses, temperatures, densities, and internal motions with a precision that had been completely impossible before. As of 2022, over 10,000 molecular clouds have been detected since the first identification of Sagittarius B/O. The Hubble Space Telescope, launched in 1990, brought a new level of detail to the study of star-forming regions. Its sharp optical and near-infrared images revealed the intricate structures of nebulae, the shapes of protoplanetary disks seen in silhouette, the delicate shock fronts of Herbig-Haro jets, and the complex interplay of light and shadow as massive stars sculpted their environments. Hubble's image of the pillars of creation in the Eagle Nebula, taken in 1995, became one of the defining images of modern astronomy and brought the concept of stellar nurseries into the public consciousness in a way that no previous observation had. The Spitzer Space Telescope, launched in 2003, carried infrared cameras that could peer deep into the dustiest regions of star-forming clouds, revealing populations of embedded protostars and mapping the warm dust heated by young stars. The Herschel Space Observatory, operational from 2009 to 2013, observed in the far infrared and submillimeter, probing the coldest dust and gas in molecular clouds, and mapping the filamentary structures within which star-forming cores are embedded. The Chandra X-ray Observatory contributed to detecting the X-ray emission from the hot coronae of young stars, allowing astronomers to take censuses of young stellar populations, even when the stars were too faint or too embedded to be seen by other means. And then came the James Webb Space Telescope, launched on Christmas Day, 2021, which has revolutionized the study of star formation with its unprecedented combination of sensitivity and spatial resolution in the near-infrared and mid-infrared. Webb's images of star-forming regions like the Carina Nebula have revealed previously invisible details, including dozens of newly detected protostellar jets, hundreds of previously hidden embedded young stars, and the fine structure of protoplanetary disks in ways that were simply not possible before. Its observations of the cosmic cliffs in NGC 3324 chronicled stars in the very earliest, most rapid phases of formation, a period lasting only about 50,000 to 100,000 years for each individual star. A phase so brief and so hidden that it had previously been almost impossible to observe. ALMA, the Atacama Large Millimeter/Submillimeter Array in Chile, has brought radio wavelength imaging to a level of detail that rivals optical telescopes. Its 66 antennas, working together as a single enormous radio telescope, can resolve structures as small as a few astronomical units in nearby protoplanetary disks, allowing astronomers to see the rings, gaps, spirals, and asymmetries that trace the process of planet formation in real time. ALMA's observations have shown that the structures within protoplanetary disks are far more complex and begin far earlier than anyone had anticipated. Together, these observatories have peeled back the veil that hid the process of star formation for millennia, revealing a universe far more dynamic, far more violent, and far more beautiful than earlier generations of astronomers could have imagined. Stellar feedback. Stars do not simply form within their nurseries and then quietly depart. From the very moment they begin to take shape, young stars exert a profound influence on their surroundings, shaping, sculpting, and ultimately destroying the very clouds from which they were born. This process, known as stellar feedback, is one of the most important and complex aspects of star formation because it creates a kind of self-regulating loop. Stars form from clouds. Those stars then modify the clouds, and those modifications, in turn, determine how many more stars the cloud will produce and what kinds of stars they will be. The most dramatic form of feedback comes from the most massive stars. Stars with masses greater than about 8 times that of the Sun are classified as O-type or early B-type stars. They are extraordinarily luminous, sometimes millions of times brighter than the Sun, and they pour out torrents of ultraviolet radiation that ionize the surrounding gas, creating vast bubbles of hot, glowing plasma called H2 regions. The Orion Nebula is such a region. So is the Rosette Nebula. So are the glowing surfaces of the pillars of creation in the Eagle Nebula. The expansion of these H2 regions does 2 contradictory things simultaneously. On one hand, it disperses the surrounding gas, blowing it away from the massive stars and reducing the amount of material available for future star formation. On the other hand, the expanding ionization front compresses the gas at its leading edge, sweeping it up into dense shells and ridges where gravitational instabilities can trigger the collapse of new cores. In effect, the massive stars are both destroying the nursery and triggering new bursts of star formation at its margins, like a wildfire that clears the old growth but scatters seeds that sprout in the cleared ground. This process, known as triggered or sequential star formation, has been observed in numerous nebulae. In the Rosette Nebula, the central cluster NGC 2244 appears to have formed first, and its expansion then triggered the formation of additional clusters in the surrounding molecular gas. Observations combining X-ray and optical data support this age gradient, with the youngest stars found near the dense molecular gas at the nebula's periphery, and the oldest near the center. Massive stars also drive powerful stellar winds, continuous outflows of charged particles traveling at speeds of thousands of kilometers per second. These winds carve out cavities in the surrounding gas and can strip material from the disks of nearby lower mass stars, influencing and sometimes truncating the planet formation process in those systems. In the Orion Nebula, the powerful wind from Theta 1 Orionis C is actively eroding the protoplanetary disks of neighboring stars, creating the teardrop-shaped propylids visible in Hubble images. Some of these disks may lose their planet-forming material before planets have a chance to fully assemble. And then there is the ultimate act of stellar feedback, the supernova, when a massive star, typically one with a mass greater than about 8 solar masses, exhausts its nuclear fuel and can no longer support itself against gravity. Its core collapses catastrophically, and the outer layers are blown off in a colossal explosion that can briefly outshine an entire galaxy. The shockwave from this explosion slams into the surrounding interstellar medium at speeds of thousands to tens of thousands of kilometers per second, sweeping up gas and compressing it into dense shells and filaments. Supernova-driven shockwaves are among the most effective triggers of new star formation. When a supernova shock encounters a dense molecular cloud, it can compress regions of the cloud beyond the gene's mass, initiating gravitational collapse and the birth of a new generation of stars. These new stars may themselves include massive members that will eventually explode as supernovae, sending their own shockwaves into the surrounding gas and triggering yet another generation. This chain reaction of star formation, with each generation of massive stars triggering the next, has been proposed as a mechanism for propagating star formation through a galaxy. With waves of stellar birth rippling outward from an initial event, like ripples spreading across the surface of a pond. Observational evidence supports this chain reaction model in several regions of the Milky Way. Groups of stars nearest to molecular clouds do indeed appear to be the youngest, while those farther away tend to be older. Exactly the pattern you would expect if star formation were propagating outward through the cloud. The large shell-like structures visible in many star-forming regions, hollowed-out cavities surrounded by dense rims of compressed gas, are also consistent with this model. Each shell was blown by the winds and supernova explosions of a previous generation of massive stars, and along the rim of each shell, the next generation is being born. But feedback is not always constructive. The same radiation and winds that can compress gas and trigger star formation can also disperse and destroy molecular clouds entirely. Once, about 2 to 5% of a molecular cloud's mass has been converted into stars, the feedback from those stars, particularly the most massive ones, becomes strong enough to begin unbinding the cloud. The ionizing radiation heats the gas, raising its pressure until it can no longer be held together by gravity. The stellar winds push material outward, and when the first supernovae begin to explode, the blast waves can tear the remaining cloud apart completely, dispersing the gas into the diffuse interstellar medium and permanently ending star formation in that region. This is why most molecular clouds are relatively short-lived by astronomical standards. They typically survive for only about 10 to 30 million years before being disrupted by the stars they have produced. During that brief window, they convert only a small fraction of their gas into stars. The rest is returned to the interstellar medium, where it will eventually be swept up into new clouds, compressed again, and given another chance to form stars. It is a wasteful process by earthly standards, but it is precisely this low efficiency that gives the Milky Way its its remarkable longevity as a star-forming galaxy. The interplay between star formation and stellar feedback is one of the key processes that governs the evolution of galaxies. Without feedback, molecular clouds would convert all of their gas into stars on a timescale of just a few million years. The observed star formation efficiency in molecular clouds is actually quite low. Typically, only a few percent of the cloud's mass is converted into stars before the remainder is dispersed by feedback. This low efficiency is what ensures that galaxies like the Milky Way continue to form stars over billions of years, rather than burning through their entire gas supply in a single frantic burst. The cosmic recycling program. There is a profound circularity to the story of star formation that is worth pausing to appreciate. Stars are born from the gas and dust of the interstellar medium. They live their lives, fusing hydrogen into helium, and, in the case of more massive stars, cooking up successively heavier elements in their cores, all the way up to iron. When they die, they return that processed material to the interstellar medium, either gently through planetary nebulae and stellar winds, in the case of low-mass stars, or explosively through supernovae, in the case of high-mass stars. This returned material, now enriched with the heavy elements that were not present in the original primordial hydrogen and helium, mixes with the existing interstellar gas and is eventually incorporated into new molecular clouds, new collapsing cores, new protostars, new protoplanetary disks, and new planets. Every generation of stars leaves the interstellar medium a little richer in heavy elements than it was before. The very first stars in the universe, forming from the pristine hydrogen and helium produced in the Big Bang, contained no metals at all. These primordial stars, known as population 3 stars, have never been directly observed, but theoretical models suggest they were enormous, perhaps hundreds of times the mass of our sun, and they burned through their hydrogen fuel in just a few million years before exploding as supernovae or collapsing directly into black holes. When they died, they seeded the surrounding gas with the first traces of carbon, oxygen, nitrogen, and other elements. The next generation of stars, forming from this slightly enriched gas, incorporated those elements into their structure and into the protoplanetary disks that surrounded them. And when those stars died, they returned even more metals to the interstellar medium, enriching it further for the generation after that. This process of progressive enrichment has been going on for over 13 billion years. Each stellar generation acts as a refinery, taking the raw material of the interstellar medium, processing it through nuclear fusion, and returning it enriched with newly forged elements, the lightest elements beyond hydrogen and helium. Things like lithium, carbon, nitrogen, and oxygen are produced mainly in the cores of intermediate mass stars and released through stellar winds and planetary nebulae. The heavier elements, from silicon and iron all the way up to gold, platinum, and uranium, require the extreme conditions found in supernova explosions or in the violent collisions of neutron stars. Each of these processes contributes its own characteristic mix of elements to the interstellar medium, and together They have built up the chemical complexity that makes rocky planets and organic chemistry possible. Our sun is a relatively recent arrival in this multi-billion-year process. It formed roughly 4.5 billion years ago from a molecular cloud that had already been enriched by many previous generations of stellar birth and death. The heavy elements in the solar system, the carbon in your body, the oxygen in the atmosphere, the iron in the Earth's core, the gold in a wedding ring. All of these were manufactured inside stars that lived and died long before our sun ever existed. We are, in a very literal sense, made of star stuff, recycled material that has been through the cosmic forge multiple times. The supernovae that enriched our parent cloud did more than just donate heavy elements. They also injected short-lived radioactive isotopes, unstable atoms with half-lives of only a few million years, into the gas that would become our solar system. The presence of these isotopes, detected through their decay products in ancient meteorites, tells us that a supernova must have occurred very close to the forming solar nebula, probably within a few light years, and no more than a few million years before the sun ignited. That nearby supernova may have done more than just contaminate the cloud. Its shockwave may have actually triggered the collapse of the cloud core that became our sun. In other words, the death of one star may have been the direct cause of the birth of ours. This is the cosmic recycling program at its most profound. Death feeds birth. Destruction enables creation. The ashes of dead stars become the raw material of living worlds. It is a cycle that has been repeating since the first stars formed, hundreds of millions of years after the Big Bang, and it will continue for billions of years into the future. For as long as there is gas in galaxies to make new clouds, and new clouds to make new stars, our own origin story. About 4.5 billion years ago, in a fairly unremarkable corner of the Milky Way's disk, a region within a giant molecular cloud began to collapse. We do not know the exact trigger. It may have been the shockwave from a nearby supernova. It may have been the compression caused by a passing spiral density wave. It may have been the gradual, patient process of ambipolar diffusion, slowly allowing gravity to concentrate gas until the gene's mass was exceeded. Whatever the cause, the collapse began. The cloud fragmented, and one of those fragments became the dense core that would give rise to our sun and everything in our solar system. As the core collapsed, it spun faster and flattened into a disk, the solar nebula. At the center, the growing proto-sun heated up, eventually reaching temperatures and pressures sufficient to ignite hydrogen fusion. Around it, the protoplanetary disk extended outward for hundreds of astronomical units, a swirling expanse of gas and dust in which the first solid grains were beginning to coagulate into larger bodies. Close to the young sun, where temperatures were high, only rock and metal could survive in solid form. These refractory materials gradually accumulated on the terrestrial planets, Mercury, Venus, Earth, and Mars. Farther out, beyond the snow line where water could condense into ice, the greater abundance of solid material allowed planet cores to grow much larger, large enough to gravitationally capture vast envelopes of hydrogen and helium gas, forming the gas giants Jupiter and Saturn. Still farther out, Uranus and Neptune assembled more slowly from ice-rich material, their growth limited by the lower density of the disk at such great distances. The evidence for this origin story is written in the rocks and meteorites of the solar system. Chondrites, the most primitive meteorites, contain tiny mineral inclusions called calcium-aluminum-rich inclusions, or CAIs, that are the oldest solid objects in the solar system. Dated to 4,567,000,000 years ago with remarkable precision, these CAIs condensed directly from the hot gas of the inner solar nebula and represent the very first solids to form around our young sun. Chondrules, the small round grains that give chondrites their name, formed slightly later and record the chaotic, energetic conditions of the early disk, where flash heating events briefly melted dust into molten droplets that then cooled and solidified in a matter of hours. The isotopic composition of meteorites tells an even deeper story. Different groups of meteorites contain subtly different ratios of certain isotopes, differences so small they can only be measured with the most sensitive mass spectrometers. These differences divide the meteorites into two broad populations, called carbonaceous and non-carbonaceous, that appear to have formed in two separate reservoirs within the solar disk, one inside and one outside the orbit of Jupiter. The implication is that Jupiter formed early enough to act as a gravitational barrier, preventing material from mixing freely between the inner and outer solar system. This early formation of Jupiter, within perhaps the first million years, is consistent with the picture of rapid planet formation suggested by the ALMA observations of young protoplanetary disks like HL Tauri, the radioactive isotope aluminum-26, which has a half-life of only about 717,000 years, has been found in the decay products of the earliest solar system solids. Its presence tells us that a source of freshly synthesized aluminum-26, almost certainly a nearby supernova, or the wind from a massive Wolf-Rayet star, contaminated the solar nebula shortly before or during its collapse. This is one of the strongest pieces of evidence that our solar system did not form in isolation, but in a busy stellar nursery surrounded by other young stars, some of them massive enough to end their lives in spectacular explosions that would seed the next generation of planetary systems with the heavy elements needed for rocky worlds, and ultimately for life. We were born in a nebula. Every atom in your body was once part of a cold, dark molecular cloud. The calcium in your bones condensed from a hot gas disk swirling around a young star. The iron in your blood was forged in the nuclear furnace of a star that exploded before our sun existed. The water you drink was assembled from hydrogen and oxygen atoms that have been recycled through multiple generations of stellar birth and death. You are not merely an observer of the cosmos. You are a product of it, a direct descendant of the stellar nurseries. And our sun did not form alone. Like virtually all stars, it was born as part of a cluster, a group of siblings that emerged together from the same parent cloud over the 4.5 billion years since their birth. those siblings have long since drifted apart, scattered by the gravitational tides of the galaxy into widely separated orbits. They are out there somewhere, spread across the Milky Way, each one carrying a slightly different isotopic fingerprint that could, in principle, identify it as a member of our sun's birth cluster. Several research groups have attempted to track down these solar siblings using precise measurements of stellar chemistry and kinematics, and a handful of candidates have been proposed, though none has been confirmed beyond doubt. The search continues, driven by the tantalizing possibility that one of our sun's siblings might also have formed planets, and that life might have arisen independently on a world born from the same cloud that produced our own. The molecular cloud that gave birth to our sun has long since dispersed. Its gas was blown apart by the winds and radiation of the young stars it produced, and by the supernova explosions that followed. Its atoms have been mixed back into the general interstellar medium, perhaps already incorporated into new clouds, new cores, new protostars forming right now in some distant part of the galaxy. The nursery is gone, but its legacy endures in every atom of every world that orbits our quiet, middle-aged, unremarkable yellow star. The quiet assembly continues. Right now, at this moment, the Milky Way galaxy contains thousands of molecular clouds, each one harboring the potential to form hundreds or thousands of new stars. In the Orion molecular cloud, in the Taurus star-forming region, in the vast complexes of Carina and Cygnus and Sagittarius, the slow, patient work of stellar assembly continues. Cores are collapsing. Protostars are accreting. Jets are firing. Disks are spinning. Planets are beginning to take shape around young suns that have not yet settled into the steady glow of main sequence maturity. We live in a galaxy that is still actively building stars at a rate of roughly 1 to 3 solar masses per year. That might sound modest, but over the billions of years remaining in the Milky Way's future, it adds up to trillions of solar masses of new stars, new planetary systems, and, conceivably, new worlds where the conditions for life might arise. The process is slow, quiet, and largely invisible to us here on Earth. But it is relentless. It does not stop. It cannot stop as long as there is gas to feed it and gravity to drive it. Eventually, billions of years from now, the Milky Way will begin to run low on fresh gas. Star formation will slow, then trickle, then finally cease altogether as the last molecular clouds are consumed or dispersed. The galaxy will age and redden as its remaining stars burn through their fuel one by one, the massive ones dying quickly, the smaller ones persisting for trillions of years as dim, cooling embers. But that is a story for the unimaginably distant future. For now, the nurseries are open. The universe is still in the business of making stars. The nebulae where this happens are among the most beautiful objects in the cosmos. They glow with the light of ionized hydrogen, sculpted into pillars and arches and bubbles by the winds and radiation of young stars. They shimmer with reflected starlight, their dust illuminated by the blue glow of nearby luminous stars. They hide vast dark regions where the densest gas blocks out everything behind it, creating voids in the star field that are not empty, but full, brimming with the raw material of future worlds. In the infrared, they blaze with the warm glow of dust heated by embedded protostars. In the radio, they sing with the emission lines of carbon monoxide, ammonia, and formaldehyde, the chemical signatures of the cold, dense gas where the next generation of suns is being assembled. And if you ever look up on a clear winter night and find the constellation Orion, and follow the line of his belt down to the faint, misty glow of the great nebula, you are looking at one of these places. You are looking at a factory of stars. You are looking at the place where 4.5 billion years ago, a cloud much like it gave birth to our sun, our planets, and ultimately to you. You are looking at the past and the future at the same time. A place where the universe remembers how it made you and practices making something new. Every star you see in the night sky was born in a place like this. Every planet orbiting every one of those stars condensed from a spinning disk of dust and ice surrounding a young stellar infant, bathed in the glow of its nursery. And somewhere out there, in a nebula we may not even have cataloged yet, a cloud is falling in on itself right now, gravity gathering gas and dust together for the first time, beginning the long, slow journey that might, in a few billion years, lead to another world, another sky, and perhaps another set of eyes looking upward and wondering where it all came from. The answer, as it turns out, is the same for all of us. We come from the nebulae. We come from the dark, cold, silent places between the stars, where gravity patiently gathers the ashes of the dead and fashions them into something luminous and new. You have been watching the entire history of the universe. If you enjoyed this video, please hit the like button and subscribe to the channel so you do not miss future episodes. Leave a comment and let us know what you think, or tell us what topics you would like us to cover next. Thanks for watching, and we will see you next time.